Okay, good morning. Good morning. Let's get started. I guess the last week before spring break, right? The homework assignment. Yeah. Looking forward to spring break. How many of you are going away from cold and going to like warm places? Not that many. Right? How many of you are going to warmer places for spring break? Very few, I thought. Okay. So do you have any questions about what we covered so far? For the homework project, right? So I hope people have looked at the homework project, and how many of you looked at the homework project? So what is it? So very few, which is still not good. What was the impression? Did it look hard or looked easy?
It looked pretty hard in that we hadn't really talked about a lot of the topics on it, and we weren't really quite sure what to do.
Okay.
Or where to start.
Okay. If you looked at it and it looked like you could do it fairly simply, right? You know, without too much complication, right? You're probably right, because I'm not expecting you to. So if you take a course in architecture, you would have to do a lot more of, you know, simulation details kind of thing, right? So once you figured out what page replacement and what gets replaced and everything, right? You can actually write a very small program to solve it, right? If you looked at the homework assignment, the homework you just turned in, right? There's some questions on what would happen if you do first fit, best fit kind of thing, right? So it's at that level of simulation. So your code shouldn't be too complicated, right? Once you figure out what are the pages, what is the page and what is the offset, the replacement algorithm is basically trying to keep track of which one should go first, which one should go next and stuff. So once you figured out what the algorithms are, implementing it in your simulation should be fairly trivial, because you're not trying to actually simulate everything, right? So for example, when you access a page, right, you have to keep track of when it was accessed to do the different policies, right? Some sort of a counter, which we'll see in the class. But it won't be as hard as what you do if you're taking an architecture course where you have to keep track of every access and stuff, right? If it's not clear, it'll be more clear when you talk about the policies. But think of how it was for the homework assignment. I think first one of the questions. It's not designed to be too hard. So if it turns out that you are making it, you're implementing a whole memory simulator for a computer architecture kind of thing, then you're on the wrong track, right? The program should be no bigger than 1 or 2 pages of C code, right? And if it looks too hard, talk to me or send me email or we'll go through that, right? So do you have any other questions? Yeah.
Could you write it in C++?
Yeah, whatever. Yeah, so yeah, you can write it in whichever language, right? I've had people write it in Perl at some point, so that I would say, please don't do it, because I don't know how many of you know Perl, but if you know Perl, that's pretty sadistic to write it in Perl, but you could, right? So whatever we covered so far, is that sort of clear, right? So we're kind of falling behind because of, I think, like we lost one of for the visitor, right? So we'll kind of try to speed up and catch up to where we should be. So far we are looking at page tables and keeping track of what pages are and stuff like that. And now we're going through different techniques to make this whole thing complete. And one of the important things you need now is to know that whether a page is valid or not, right? So this should be known by the hardware and controlled by the operating system, like most stuff in the memory module, right? So essentially the problem here is, given that your logical address could be fairly large, if you have a 32-bit architecture, it can be up to 4 gigabytes per process. Your page table has to technically be able to store all 4 gigabytes of space. But practically, your applications may not be using certain pages, right? So when you try to access those pages, you need to get segmentation for your page process has to be killed, or something has to happen. So if you try to access a page which is logically in your logical address, but has never been allocated, so there is no physical page mapping to it. So you have to know what those pages are, and the hardware gives you your ability to do that using validity bits, right? In fact, hardware gives you a lot more facilities than this, and we'll see what those are later on. But essentially, what these are if the hardware notices something which is not right, it'll give you a fault, and you can deal with that, right? The simplest one is a validity bit, which says that whether that particular entry is valid or not. You can have more complicated ones, such as read only, read write, write only, or execute only, and so on. So those are ways to protect your pages from certain kind of operations, right? And we'll use those in the subsequent sections. But for now, the simplest stuff is validity bit on the page table, which tells the hardware whether it's valid or not. If you try to read that particular page and you have the validity bit not set, then you get a page fault, and it's up to the operating system to do whatever, right? So conceptually, this is how it looks. So over on the left, you have your logical address, and this is your page table which maps it, right? So logical address page 6 and 7, though if your process could have them, right now they're not allocated, so there is no mapping, there is no corresponding physical frame for those. So the validity bit for them are set to be I. So if you run a program where it tries to access logical page 0, 1, 2, 3, 4, 5, right? Your program will go through fine without the OS ever getting involved, because the OS set up this page table. So it'll go through fine. If your process ever touches on logical address 6 or 7, right, your hardware knows that those are not valid. So your hardware will give you an interrupt, and you either give a segmentation fault or you do something else. And we'll see what something else are later, right? The key is you can use these to bring the pages in and out on demand. But for now, you'll do something with that, right? Is that clear? And those are important fields. And depending on, so these all depend on what the hardware can provide, right? And your operating system is using what the hardware provides to make things better, right? So the more complicated the validity, the bits are, the better you can do certain techniques, right? How would you? So if you didn't have a validity bit, how would you solve this problem, where there's a certain logical addresses which have no legal physical address mappings? How else would you solve them if you don't have a hardware supported validity bit? Yeah.
Could you go through the page table and remove them? Remove the addresses? So they're not even there?
You can't remove. So the page table has to be the whole stuff, right? So the page table has to be the whole address space. So the page table cannot be made smaller, right? Yeah. So you have to put something illegal there. So when you try to access this, then you'll get something, right? So it's not clear what is an illegal address, right? So in this example, you have an address of 0, right? Which you know it's illegal because it's of the context. But there's nothing illegal about it because it could actually map to physical frame 0, right? Yeah.
Can you put negative values in the page table?
So going back to binary arithmetic, right? Negative values are basically the 32nd, the most significant bit is 1, right? But as an address, there's no negative because all of them are addresses, right? That's clear, right? Negative addresses are really only if you look them as a signed integer, but as an address, it's a higher bit is set, right? So you can't use negative addresses. You can't use 0 because even in this example, 0 is a valid physical frame, even though there's no useful things there.
I mean, you can just put another bit. It's using extra space, but there's not really any clean solution other than just having an extra bit to tell you.
Yeah, if you don't have a hardware giving you this solution, there's no clean solution, right? It's essentially you have to, in software, validate every address, right? Every address which is going to be made, you have to make sure that they are within the range, right? So most modern systems, if you don't have the validity bit, you are it's taking such a performance hit that this is such a basic form of the system. Yeah.
Okay, I'm just trying to understand this diagram correctly. On the left, the pages 0 through 5, are those only for a single process?
Yeah.
Okay.
Yeah, so for each process you have a page table, right? So the page table, yeah, so the page table is a per process concept, right? So that particular process, the logical address of the process can have, let's assume, goes up to 8 pages, right? It's a 4-bit, 3-bit address space, right? So logically, you could potentially have up to 8 pages, but at this moment, it only has 6 allocated to it, right? So in the future, this process somehow can ask for another logical page, and that could be allocated and put in the frame 6 or so, right? And it will be valid, right? So without restricting the application from ever going past a certain size, you have to have some way of knowing that if application touches on page 6, you need to do something, right? The key here is you want the OS to be as hands-off as possible. So if it did this page table and all those things, you set up this table and you let the machine go. The OS is not involved. It doesn't care what addresses you are using and all those things, right? Because what your application can do is, let's say, load, right? Let's say this means that you're loading something from logical page table 5 offset 10, right? Your program could do something like this too, right? Your program could be doing this. So the only way, if the hardware is not supported, is the OS has to look at each instruction and see, okay, this is not valid, because it has to look at the table and all those things, and that will slow down your program tremendously. Whereas you can run this application on this particular table, and the moment you hit this, you'll get a page fault saying you're accessing an invalid bit. And what you do with it is up to you. And we'll see good uses of it and bad uses of it, right? Bad uses would be you'll kill the process because you're trying to access something you're not supposed to access, segmentation fault sort of thing, right? And the other bits that we will see in the future are read only, where if you try to write into that address, you get a fault. If you try to read, you're fine, right? So if you do a load, some sort of like a load, you're fine. If you do a store, then that's not fine, right? So you can have read, write only, right? You're only allowed to write but not allowed to read. And then you're allowed to do execute, right? And combinations of those, right? So you could potentially put execute bit on the text piece so that you can only run the objects that are part of the code, right? So one of the code I emailed to the class on how to change your memory address itself to a program, right? You can use some of these to protect against that. You can say, don't run a page which is not set to the execute bit, and the only OS is allowed to set execute bit kind of thing, right? And then we'll see those as we move forward, right? So far, we have looked at some of the ways of dealing with the page table and all those things. So remember, so for every process, there's a process table, right? And we notice that the process table tends to be large, right? Especially as you go to more modern processors with a lot of address space, it can become a really big problem. So if you take a 64-bit address space, right, which most desktops and most servers moved for a while back, and most of the Intel machines are going towards the 64-bit processors, right? That means your address space is 2 power 64, and if you use a 8 kilobit page size, right? So that's 2 power 13. So you may get 51 or some really large number of page table entries, right? And if you think about it, that's in gigabytes of memory for your page table, right? So even for 32-bit processors, it was horrible. I mean, the page table size was big. But when you go to 64, it's stupendously big. So you can't really keep one page table for every process in the full fashion, right? So some of the techniques we look at, hierarchical, hashed, or inverted page tables, trying to address the problem of how do you keep the page table manageable, page table size manageable and small, right? The key here is logical, the addresses that you're using, it's fairly large, but the physical address is fairly small, right? So even though you can potentially have a very large physical process table, practically you don't need to store all the stuff because it's mostly going to be empty, right? So 64-bit address space can give you what, 16. What's 64 in? Yeah. 6? Yes, it's 2 power 60, right? Which is 10 power 18. Sort of, right? If you look in decimal, right? Something like that, right? Let's assume 10 power 18, right? That's a large memory, right? None of us are going to be having that much of main memory in any machine that we get, right? That much physical memory is not going to happen. So that's why we are able to do this stuff, right? In the future, if we actually have, if you build a machine which has that much of main memory, then many of the tricks we play cannot be done because the logical address space may have to be used on that particular machine, right? So the first way to solve this is to use hierarchy, right? And hierarchy is a solution that we use for other concepts like directories and stuff. So if you have lots of files in your machine, rather than put everything into one directory, you kind of put them into hierarchy, right? So each directory is small, something that you can manage, right? So actually, let's look at the figure. So rather than having one large page table, we create outer page table and inner page table, right? Where the outer page table, there are fewer of outer page tables. So there are only certain entries that need to be filled for the inner page table. And that way, you have to have the outer page table, which is completely as big as what you want. But the next level page table is sparse, right? There may be entries which are not valid on the outer page table, right? So let's go back to the actual math of how we do that, right? So if you take the, let's say 32-bit address space, and let's say you say 13-bit is the offset, right? Like we had before, and this is the page table size, right? So what we do is we split this off at some, let's say this is M and N, right? And this is the outer page table size, and this is the inner page table size. So for every logical address you have, you figure out, you split these stuff to know which outer page table and which inner page table you would access, right? And the key here, the main reason you can get away with that is these things you expect them to be clustered together, right? You don't expect your program to be using a logical address which is all over the space. You expect them to be kind of clustered because that's how you allocate memory. So you expect that this should be able to cut down a lot on the number of pages you need, right? So depending on whatever this is, your page table now has to be able to store at least this much, and depending on how much you get allocated, you have those, right? So going back here, so your outer page table may have entries where this is not valid, this is not valid, this is not valid, this is not valid, and this points to a whole bunch of pointers, some of them not valid, some of them not valid, and these point to the actual frame kind of stuff, right? So this way you cut down on the number of pages because you saved on this, and this subtrees, right? What's the negative aspects of doing this? Yeah.
If you don't have a hardware component or something like that, you have to access memory one extra time, so
Yeah.
you can slow it down.
Remember, this is in a critical path, right? Every address every memory lookup you do has to go through all the stuff, right? Now you have to keep the outer page table in some sort of cache, and the appropriate inner page table in some sort of a cache, because otherwise, in the worst case, you may have to go to the outer table, which has to be read from memory, and then you have to read the corresponding table, which has to be read from memory. You can't do them in parallel because you have to read the outer table to figure out which inner table to read, and then you have to use that to read the actual memory. So you can actually add one extra memory lookup, right? And that could that can really destroy your program, right? So yeah, when you do this lookup, you split the logical address on the top into P1, P2, and D. But P1 tells you which outer table entry you should look at, and then the P2 tells you which entry within that outer table you should look at, and so on. So if all of them are in cache, you get good performance. If some of them are not in cache, then you tend to get slower, right? So that's one way of doing the stuff, and the bad part is you may have to keep a whole bunch of stuff more in memory. The other way to do is to hash them, right? So we know there's a big logical address space, and we have hopefully a smaller page table, right? And we assume that there are only few entries here which are useful. So we define a hash function, right, such that you take this logical address, send to this hash function, it'll hopefully map into something. So let's assume that this is valid, this is valid, this is valid, and this is valid. If you had an ideal hash function, it could map like this. Right? This way you get better compression. So how many of you know about hash functions? I'm guessing you should have picked up in data structures, right? So what happens with the hash function if things are not so good? Yeah.
You have a lot of collisions?
Yeah, you have a lot of collisions, right? So I didn't say what should happen here. So this may have a collision where this could map to the same thing, right? It could map to the same entry. And the way you deal with that is to have a bucket data structure. So basically you say, if they say this is 0, 1, 2, 3, 4, 5, and 0 and 1 fit in here, right? So you do a hash to figure out which bucket you should go into, and then you do a sort of a linear search to figure out what that entry is, right? And the usefulness of the system depends on the hash function you're using here. Because if the hash function is bad, all these addresses could map into a single bucket, and they are doing a linear search on those, right? Which is horrible, especially since you're doing this for every instruction. And if it happens to be good, then it could turn out to be good for you. But the harder part is this hash function has to be a hardware implemented detail, not a software kind of stuff, right? So this hash function should be good for all applications, regardless of what your application would do. Because the logical addresses are created by applications, the hash function is done by the hardware, right? So depending on how well you do this stuff, it could turn out to be good or turn out to be bad, right? Just with any other hash functions, right? So that's a way to deal with those. So conceptually, you take the logical address, you do some sort of a hash, and you come up with a hash table, right? Hopefully the hash table is smaller than your real page table, but the problem is you have overflow buckets. So if you have collisions, you have to search through them in some fashion to figure out what the physical address is, right? So the last technique, which is really used for, so the previous two techniques sort of work for 32-bit processors. It does not work for 64-bit or 128-bit addresses because those are so big that whatever hash you can do, you still don't bring it to a sane size, right? It may bring it down to 4 gigabytes, which is still way big for most machines, right? So the next technique really solves the problem of the page table size by making it extremely complicated, right? It's called an inverted page table because the page table now no longer keeps track of the logical addresses, rather it keeps track of the physical addresses, right? So here, you assume, let's say this is the logical, and this is the physical, right? Rather than keep track of all these items, now your page table keeps track of your physical address, right? And you have one page table for the whole system. You no longer have to keep track of different page tables for the different system. Now it says that so you have to keep track of which process the entry means, right? And you have to say for this, so this particular physical frame is being used by this particular process. And the entry here will give you the logical address, right? It says that, let me give some numbers, right? So let's say 0, 1, 2, 0, 3, 4, right? So this is the process, and this is the logical address. What this means is for each physical address frame, this one says that this physical address frame belongs to process 0, and the logical address that the process has is, let's say, 100, right? Which is a pretty efficient way of storing stuff, because this can no longer be bigger than the your actual physical memory. There is one table for the whole system, so the page table, you solve the space constraints, right? The problem is, when you're really using a system, you don't really care about this. You're caring about this, right? So here, I'm saying I am process 0, right? And I need logical address 100. I want to know where the frame is. What this page table has is that there is one entry here which says that process 0 has a table of 100, right? So the way you solve this is you have to search through this whole table for every instruction to say, does the process match with what my current process is? And if it's yes, does the logical address on that particular entry match what I'm looking for? If they do, then the physical address the frame is the one matched here, right? I think I have a graph to show that, right? So even though it looks simple, the key here is the search part, right? So if you look at the page table now, it has to keep track of which process, because you have one table for the whole system depending on which process is running, right? One table to represent the physical memory, and for each of the frame you say which process it belongs to and what's the logical address that the process knows this address as. So, but even though it's set up this way, you're using it from this side, you're using it from this side. So when you want to use this stuff, right now you have to set the process ID to the hardware, so the process knows what the process ID is, right? And it knows it's looking for P, so it searches this table looking for the entry P, right? And it happens to find it at offset I, so it knows that the physical address is really I, right? Does that make sense? So this could be horribly slow, because like that search component, depending on how you do it, it depends on how you do the search, right? And how would you do the search? Can you think of techniques of how you could build the search? We looked at one technique before, right, on the paging stuff. Could you use something like that? You're talking about TLBs, right? Could you use a TLB data structure to solve this problem? Could you use a TLB for this entire page table? Yeah.
Well, you could have like separate TLBs for each process or something, maybe.
We did that before, right? But in this case, you can have one. If you put this whole thing into a TLB, right, then you can solve this pretty sweetly, right? You can know in one clock cycle, essentially you can search all these items, right? Yeah.
So in this case, when you have like different processes, wouldn't you have to change your TLB like construct to
Oh,
process still and everything?
So in the previous context for how we are looking at it, yeah, TLB is per, I mean, you have to change it per process and stuff, right? But I'm saying in this particular construct, in this particular fashion, if you could build a TLB which can hold this page table, then this whole problem is solved, right? You can have one TLB for the entire system that can search and find you based on the PID and the P to tell you where it is, right? The problem is this page table is still big, right? And building a TLB which is that big is not possible, right? So for example, so the page table has to be able to hold all the page frames in a real system. So assume that your real system has 4 gigabytes of memory, right? So 4 gigabytes memory is like 32 bits, right? And depending on what your page table and stuff, what your frame size is, right? If you assume a frame size of, let's say, 1K, you still have 2 power 22 entries, right on the. Does it make sense? If you assume a 32-bit processor, and if you assume 1 kilobyte per frame for the frame size, right? So that means you need 2 power 22 entries for this page table, right? And which is 4 million, right? That's 4 million entries for this page table for a 32-bit machine, right? If it's 64-bit machine, right, all bets are off. It's essentially 2 power 54, right? You're not going to be able to build a 2 power 54 size TLB, right? You should be very happy if you have 128 entry TLBs, right? I think somebody of you mentioned that you're taking architecture course, right? Where you're going through TLBs. What's the biggest TLB entry size that you guys look at in the class? TLBs are horrendously expensive to build, right? If you have few entries, you should be happy, and so that's what differentiates between your desktops and the server, right? The servers have more, but nowhere near to this one, right? Which means that you have to have other mechanisms to search through this stuff, and all of this have to be done by hardware. So from an OS perspective, we don't care how you do it, but the hardware has to have some mechanisms to search through this stuff really quickly, and that's not a trivial task for them to do, and you have to do this very fast because every instruction has to go through the stuff, right? So they use a whole bunch of stuff and to solve this problem. Unfortunately, whether you like it or not, when you go to the 64-bit or beyond, you have to do something like this because otherwise you can't manage the page table size entry at all, right? So the good news is this is all hardware, folks. We have nothing to do with it from an OS perspective. The bad news is if the hardware folks don't do it well, then your machine would be so slow that people would blame the OS for it, right? So towards the end, we'll see a little bit of how the Intel architecture actually does that. So they have a mixture of both of these. The newer 64-bit machines use some of these inverted page tables with certain caching to make this stuff go faster. But I hope you appreciate that caching means that if you use a page over and over again, you can do something, right? So if you keep using the same PID and the same P, right, you could cache that somewhere. But if your process is going all over the space, right? So if you wrote a code which randomly operates on some data structure, you could have a terrible performance hit, right? So if you have a large memory location chunk, you can write a code which goes through them sequentially, right? In which case, some of the caching stuff may work. But if you randomly go all over the place accessing different items, then you can potentially pay for each memory instruction. You do the search overhead, so your system can go really, really slow because you are writing code a certain way, right? So that's the key thing to remember. So you can write if you write code without understanding what the hardware is doing, right? At this point, the OS has nothing to do because OS is not really involved with the search mechanism. But if you don't work with the hardware, then your system can be really bad because every instruction would now have to do this search, and that can be horrendously slow, right? So I'm going through some of these the techniques which kind of fit into the larger scheme. The other scheme that is important is, so far we kind of looked at each process having its own page table, having its own logical address space and physical address kind of stuff, right? There's no notion of sharing. But you don't want to do that all the time because many of the times lots of data can be shared, especially programs and C libraries and so on. So having these page table entries really does help us in terms of sharing, right? So most programs have shared data like your C libraries and all those things, and private data which you don't want to share with anybody. The way you solve them is to make sure that all the page table entries for all these processes point to the same physical frame, right? So you have one copy of code which is used by a whole bunch of different processes, and each of the process table entries, the page table entries should point to the correct one. So here's a example, right? So in this case, there are three processes: process 1, process 2, and process 3 in blue and white and gray, right? So they all use the first three logical frames: ED1, ED2, ED3 is shared, right? So you have to map them into the exact same address, because if the process does, if the code here accesses something, it has to be the same. You are free to use different the data entries is different for each process. Data 1, data 2, and data 3 are different for different process, right? So if you look at the page table entries, the page frame 3, 4, and 6 is constant for all the three processes, right? The logical address 0 maps to physical frame 3 for all the three processes. Logical frame 1 maps to 4, 2 maps to 6, right? Logical frame 4 maps to different things. If a process 1, it maps to frame 1, process 2 maps to 7, process 3 maps to 2, right? So this way, you only have one copy of contents of 3, 4, and 6, and they're being shared by all of them, right? So this is how we would start doing sharing. So once we start to do sharing, the notion of validity bits really come in handy, right? So this way we can make sure that nobody's able to write, nobody's able to read, people are only able to do some things by changing the bits. But for now, right, this is how you share the piece of code between three processes, right? Is that clear? So what are the bad things that can happen if you're using such a scheme? Yeah.
And for some reason, one of the copies gets like one of the processes alters the copy of the shared data you have. Usually the rest of it, like if you had a self-modifying code or something that mapped the wrong address space and wrote.
Yeah, I mean, unless you explicitly want the self-modifying code to be seen by others, right? You have to have ways to protect it. You have to have ways to make it read-only or some other protection, because otherwise, if process 1 modifies these shared pages, right? Process 2 and 3 may see these modifications, even though they may not actually assume that they're sharing, right? So in this model, we're not talking about explicit sharing like what we saw from processors. These are implicit sharing. The users did not really know that they're sharing this code, so you have to make sure that those are properly protected, right? So the next aspect is segmentation. I'm going to go through them really fast because this is how we kind of started out, right? The notion of paging says that we don't want to deal with external fragmentation. We convert the problem of external fragmentation to internal fragmentation by giving all the page allocations in one size that you wanted, right? The notion of segmentation, which I kind of alluded to before, is the notion that we originally started with, which is the applications require different size chunks. They don't really care about the ways that you use to save on external fragmentation, right? The notion of segmentation goes back and says, you ask for whatever you want, and we'll deal with it somewhere, right? What is different here is, now that we know paging, the way you implement segmentation is really by using paging, right? So application would ask for, let's say, two segments, right? And the way you implement that is, you still have fixed size pages, right? You ask for a segment which may consist of many pages. From an application perspective, you're dealing with segments. From a system perspective, you're dealing with pages. All the stuff that we looked at for paging applies here. But from an application perspective, you're dealing with segments, right? You're thinking in segments, even though segment really is stored as paging. From an application perspective, you assume there's going to be external fragmentation, right? There is, but only for the last page, right? So real systems use segmentation, right? But it's implemented using paging in most modern machines. So from a system perspective, you ask segments for your main program, your different functions, your stack and heap and what have you, right? So you ask for them as a structured concept, because you say, I want to keep my code. I want to bring my C library, right? So C library is in one segment, but underlying it's all implemented in paging, right? So I'm going to go through them fast because it's essentially applying all the paging concepts with the notion of segment as a way for users to deal with them, right? So with this, what will happen is your logical address space is no longer assumed to be contiguous from 0 to n. Your logical address space, so if you look at a modern process, right? And this is the logical address space for a process. So it may have, this is valid, this is valid, this is valid. There are some chunks which are valid, right? And this is the text, which is the program. This is data, and this is like stack, and so on, in different logical segments. And all the ones in the middle are not valid, right? But it's implemented as a page table concept, except from application perspective, you think of them as 3 segments which are hanging in space, right? So this is what your program's view is. You assume you have main functions, some libraries and stack and so on and so forth. Each are of different size depending on what your application, essentially what your compiler creates for you. But in the physical memory, they are stored as different pages, because those are easier for the operating system to manage, right? The same things we said before. OS no longer has to keep track of how much you are asking for. It can give you in orders of frames, right? So you have the notion of, so when you keep a segment table, you keep track of the segment start and the segment end, even though they get translated to page concept within the hardware, right? And all of this support are done by hardware, and many of these things, if you don't have hardware support, you can't really do it in software, because every access to a memory location will have to go through these processes. So if the hardware does not provide segmentation registers, then you can't really do it, because it'll make the system so slow. So you have all the concepts we talked about. You can do a relocation, because essentially you deal in segments which map into page table entries, right? You have the sharing with the same way as before. Essentially, you share a whole bunch of pages together or not. From application perspective, you say, I want to share this segment. You translate that to sharing a whole bunch of smaller pages internally. And allocation, you can allocate them contiguously or not, because the pages are the ones which are being allocated, right? And the same notion of protection, because if you say you want to protect a segment to be read-only, you make all the pages that form the segment to be read-only, valid or read-write, and so on and so forth. So yeah, so you have a notion of segment, and you say what's offset within the segment. Then you map the offset within the segment to the offset within the corresponding page table. So you find which page table entry has the segment that you're looking for, and then you find the constructs, right? So I'm going to go through them quickly because essentially it's no different except you have a higher level concept, right? Which is sort of where we started. So the multics, which is the logical parent of Unix, used segmentation with the page table underneath to from an application perspective, it looked like segments. From a hardware perspective, it looked like paging, right? So within the multics notion of address translation, the OS keeps tracks of segments. So from the segment, you figure out what page table you should have, and then from the page table, you figure out what the address is, right? So this is essentially a way of implementing segmentation using page tables. So it all boils down to what the hardware can do, and here's one of the hardware entries for Intel 386, right? So Intel 386 essentially is a segmented architecture, right? So it has a notion of a segment, right? So you figure out what the segment descriptor is, and from that you figure out what the corresponding page table is. All this is supported by the architecture, right? So if you look at the assembly language for Intel, you have a notion of a segment register and the address, right? And this is the logic it implements, right? So if you write a code using segments, it's easy to translate them to Intel architecture because the architecture knows about segments, but it manages the segment tables which the OS still fills, right? So you get the concept of a segment with implementation of a paging, right? Yeah.
Are pages all the same size?
Yeah, that's the definition of paging.
How do we decide on the page size?
So the page size, I think we kind of mentioned. So if it depends on what you expect. Right? So if the page size is too small, then your page table will be large. So you kind of find a good match. And the good compromise also depends on what the hardware can provide for you, right? So if the hardware provides you only up to 8K, then you're kind of stuck with it, right? But you have a narrow range, I think from 512 to 8K, depends on how much memory you have and stuff like that, right? So yeah, from an OS perspective, it's easy to manage with fixed size stuff. From an application perspective, you want different segments. And again, if you have a larger page table, you have a lot more internal fragmentation. So you have to weigh that too, right? Usually you don't have much choice because the hardware tells you can only do 8K, and you kind of go with that, right? And I'm gonna defer this. We'll look to see what Linux is doing later on, right?